Welcome to Chapter 6 of KBOCC Earth Science/Geology. In this chapter, we're going to be discussing volcanoes and other mountains. Here's a quick breakdown of the table of contents. We'll start with a conversation on the volcano commandos. Go into magma, specifically viscosity, sources, and composition. Narrow a conversation into Mount St. Helens. Expand out from that to the products of volcanic eruptions and the landforms associated with them. Talk a bit about mountains, and then mountains' relationships, temperatures, rise, fall, isostasy, things along those lines. So, as a scientifically literate citizen, what three questions would you ask about this volcano if you moved to the city of the foreground, Tacoma, Washington? You could probably think of a lot of questions you'd ask, right? Key of those would probably be, is it going to blow up? But there's other things related to volcanoes and volcanology that are of very interest to the people in this city. How do they relate to earthquakes? How does it relate to the soil composition? How does it relate to the weather, right? There's actually a lot volcanoes do to interact with people that surround them that are vitally important beyond them exploding. Global volcano statistics. There are about 1,500 some odd active volcanoes worldwide, as this map shows us. A third have records of previous eruptions. Humans have seen about 500 some of those volcanoes erupt. And we get about 2 to 3 eruptions per decade that you could probably classify as a major disaster. Interesting note, 500 million some odd people live near an active volcano. A lot of people live along those red dots there. And fewer than 200 volcanoes have instruments to assess potential for eruption. So of those 1,500 volcanoes, and of those 500 or so that have erupted in recorded history, 200 or less actually are being actively studied and watched for. So there's a lot of people living next to volcanoes that we know nothing about. And that's interesting. So let's start by talking about this volcano here. I don't speak Spanish. I apologize if I screw up these words. The Nevado del Ruiz volcano in Colombia had a volcanic mud flow in conjunction with its eruption that killed more than 23,000 people. 23,000 people ran over by mud flows in association with the volcano. That is astonishing numbers of people, right? Geologists from the VDAP, the Volcano Disaster Assistance Program, can help identify these risks and hopefully prevent loss of human life and property as a result of them. Here we have a nice picture of 9:08 p.m. where you see the smoke coming out there from the center top of the picture. The ice and snow up there are affected by the volcanic eruption, right? Volcanoes, you're probably picturing them, they're hot, right? That's a known thing. So when the volcano starts to erupt, starts to outgas, as shown in these pictures here, there's also there's kind of smoke everywhere all over this picture, actually. That ice and snow will start to melt, mix with the mud, mix with the sand on the side of the dirt on the side of the volcano. Lo and behold, mud flows downhill, right? Downslope, filling river channels, causing what we're looking at here. The center of that picture is a town, right? 11:30 p.m. You go 2.5 hours from eruption starting to an entire town decimated. And again, look at that, 46 miles away from the volcano. 2.5 hours have mud flows fly off of this volcano, travel 46 miles, 74 kilometers, and destroy a major town. That's how 23,000 people die from a mud flow. Buildings carried away, and mud flows up to 16 feet deep. Massive, right? If no one's watching the volcano, how are you going to know this thing's coming at you at 46 miles in 2.5 hours? How are you going to know, right? So let's look at another volcano. This one's in Africa. Here we have, I'm not even going to pronounce that. This volcano in the Democratic Republic of Congo. So I have no idea how to pronounce that one. Scientists have looked at the results of these volcanoes and studied previous lava flows in the bedrock of this area to determine what happened. Because what you're looking at here, this is going to be a mud flow in the geologic record as time progresses. We talk a lot about the rock record, the geologic column, right? You're looking at a new section of it being formed today, or rather some time ago. Right? That volcano in the background is gigantic, and you can look at the results of it both in the past, older lava flows as shown here, right? Here we can see on the left of that bottom picture previous lava flows, and the right new lava flows. See where flows have gone, see where flows might go in the future. Help protect the people surrounding this lava flow so that this stuff doesn't damage them, right? Because loss of buildings is one thing, loss of life is incredibly different. So let's go back, talk about VDAP, the Volcano Disaster Assistance Program. This is a group of scientists that traveled to the Congo, specifically to examine this eruption of this Congolese volcano in 2002. They studied the lava flow in the nearby city of Goma with almost 500,000 residents. And they found part of this lava flow, right? When we talk about lavas and igneous rocks in particular in chapter, what was that, chapter 4, I believe? We talked about igneous rocks or previous lavas having gases trapped in them from the process. Well, these toxic gases were actually trapped in a lake, a nearby lake in the Congo, that were not released at mass. But these gases were still leaking out. And as shown here, the poisonous volcanic gases from this lake here was responsible for killing 1,700 people in the surrounding villages. The lake itself was releasing poisonous gases from lava flows. So it's important that the Volcanic Disaster Assistance Program, VDAP, is important that scientists go in and understand and assess volcanic hazards, because it's not just the eruption and the lava that can get you. It's the mud flow, as shown here in Colombia. Thank you. Mud flow shown here in Colombia. It's the volcanic gases shown here in Cameroon. This volcano in the Congo, they needed to know how everything's going to play a part, because as it says here, right, the volcanic gases that killed 1,700 people in Cameroon are trapped in Lake Kivu down here at the bottom from not only those new lava flows that flowed down past the city of Goma, but previous lava flows and where they traveled. Assessing all the risks of a volcano is vitally important. So now that I've scared you a bit with what the world is like with volcanoes, let's backtrack a bit and talk about the components of volcanology and volcanism, specifically magma viscosity. So we just discussed gases in volcanoes, right? The more gas that is trapped in a magma or lava, the liquid part of the rock, right, the less and more viscous it will become. Viscosity is resistance to flow. A highly viscous fluid flows poorly. Think syrup, think molasses, think honey. Honey is highly viscous. Water, gasoline, things like that have low viscosities. They flow easily. So the amount of different components in a magma or lava, magma being molten rock below the surface, lava being molten rock above the surface, the amount of different constituents within a magma affect its viscosity and therefore affect how fast it moves and how much damage it can do. And here's the picture of the viscosity that I was talking about. As you can see there, the lavas, basalt lava and rhyolitic lava at the bottom there, have very different consistencies. Basaltic lava can flow like, let's say, corn syrup to peanut butter. right? Whereas rhyolitic lava can flow like a tar, or even slower than that. Very different levels of how things move. So gases, as I said, are a major component of magmatic composition, or what's in a magma, what's in a lava. We call those things volatiles. And there's other parts of a magma lava besides the rock, of course, that can affect its viscosity, affect how it flows, affect how it behaves. Water vapor, carbon dioxide, sulfur dioxide, water itself. All these things can commonly be found in magmas, and the different levels of them affect the way the magma behaves. You can almost kind of think about it like a carbonated drink, if you will. Since magma is or lava is a fluid, it's going to have gas in it. As the gas releases out of your soda pop, that's the same way that gas is released out of these fluids like magmas and lavas. As usual, I say this every single time, right? You're probably getting tired of me saying it. I'm not going to do the concept tests, but I will stop so you can read them yourself and try to answer the questions if you find that useful to your studies. So, been saying this a lot, right? Viscosity depends on magmatic composition, what the magma is made of and what is in the magma. If we go back to our conversations on igneous rocks, we talked about mafic and felsic rocks, or the amount of silica material, element silicone in the constituent material. If you have less silica, less silicone, less oxygen, you have lower viscosity, meaning faster flowing material. More silica is higher viscosity, slower flowing material. So combine that with what we've been talking about previously with the volatiles like water vapors, carbon dioxide, what have you. You can have a very amazing mixture of different types of volcanic volcano output, right? There's a lot of stuff going into this combination. Not all lavas, not all magmas are the exact same. Here we can see here, basaltic lavas tend to be very low viscosity. They also tend to be very high in temperature. The two are related. The hotter something gets, the faster it moves, right? If you've ever done anything revolving around like syrup production, you boil the syrup to remove impurities in it, and it gets very watery. Then when the syrup cools, it becomes this thick stuff that we put on our pancakes. Rhyolitic lava flows, these are your felsic rocks, your granites and rhyolites, right? These have a very high viscosity, in part due to their very low magma temperatures, but also due to the high silica content. The more silica in there, the more silicon oxygen in there, the more it sticks, less it wants to flow. Another concept test. Feel free to pause if you like. So when this volcano, this one here, happens to erupt, there's a whole lot going into what comes out of the volcano besides just molten rock, besides fluid-like rock. The type of rock it is impacts how far it goes, how fast it goes, how explosive it is, how much it burns everything, right? There's a lot to these conversations. Furthermore, well, on that subject, actually, the more viscous the material is, and remember, viscous things are such like rhyolites and granites, the more violent the eruption. Gases can escape easily during mild eruptions of low viscosity magmas like Hawaii, right? Hawaii is kind of always letting out magma, but it's not exploding at any severe level. But if you have a highly viscous material, gases escape more explosively because it takes more pressure to release out of the magma or the lava, and so you have a more highly explosive eruption. We find those in Alaska, think Mount St. Helens. So go back, is this an explosive or a less explosive volcanic eruption? Based on that, more explosive, less explosive, do you think we're looking at rhyolitic lavas, andesitic lavas, or basaltic lavas? What temperature is that eruption? What byproduct are we going to have once the magma or the lava cools? Cool. So here is that volcano map again. And notice we have yellow triangles on known famous volcanoes. Of course, Mount St. Helens up top there, but also the Nevado de Ruiz volcano in Colombia, Mount Vesuvius, of course, Pompeii, right? Krakatoa, lots of big stuff there. Something we want to point out, and we've talked about this map a lot, right? But these red dots correspond very directly with divergent plate boundaries and convergent plate boundaries, places where plate tectonics is happening. There are a few exceptions, right? Hawaii being an obvious example of a hotspot, which I believe we've talked about before, but volcanology and volcanoes are associated with plate tectonics. We've talked about that a lot in previous chapters, and I can go deep into it. So, magma sources. Where does magma come from? Well, the deeper you go in the earth, as we discussed, the hotter it gets, right? And the earth is under a lot of pressure from the energy inside of it. The release of the energy is tectonic plate movement, and the release of the energy, sort of like a pimple popping, if you will, is volcanic releases, volcanoes, things like that. Mantle rock comes up, pushes things around, and the boiling of that mantle rock needs to go someplace. Eventually, it comes out of volcanoes mostly. Talked a bit about this before, basaltic and rhyolitic compositions. These revolve around kind of where the volcano is as much as what's underneath it. We tend to find basaltic magmas in oceanic ridges and hotspots on the left here. Your rhyolitic and granitic magmas are results of the partial melting of the continental crust on the right, giving you a different magma composition, right? Your darker rocks, your mafic rocks, or oceanic rocks, like your gabbros and your basalts, and your granites and your rhyolites are your country rock, your host rock, your crust, continental crust, over here on the continental lithosphere. And again, when we pay attention to where the magmas are coming out of, we notice this exact condensation here. Hawaii, basaltic magmas. Iceland, basaltic magmas. Start approaching into the country. It's like in Africa, there's a rift zone, you get basaltic and rhyolitic magmas. And you start approaching more rhyolites and more felsic rocks as you enter the continents. Andesitic rocks would, of course, be a halfway in between. Those are your intermediate rocks we talked about before, your andesites and your diorites. And they're just what happened to have melted to create the magma that then came up. The more country rock, the more crust that melts, the more felsic the overall composition of the magma, and therefore more felsic the overall composition of the igneous rocks will be. Again, felsic being the low silica count, as we talked about before, your rhyolites and your granites. Partial melts. So another cool thing about volcanoes that when you learn about it, makes them much more interesting is that volcanoes, first of all, there's lots of different volcanoes. We just talked about that, lots of different magma sources, but the same volcano is not always going to erupt the same material. Examples of that we call partial melting. This occurs when some minerals in the rock melt while others remain solid. Because all the minerals are different, those like 500-600 different minerals that we commonly see, all of those have their own unique chemistry and their own unique response to things. So when you say melt a magma to define silica content, such as a partial melting of the asthenosphere, mantle, wedge, or continental crust, this will generate a particular magma type, basaltic and andesitic, rhyolitic, with a corresponding silica content, low, intermediate, high. And that process will give you the variety of melts that we have, right? Going back to this image, I guess, but more so this guy here, all of those correspond to different things that melted at different levels at which the melt happened, different places where the magma and lava originated, creating that wide variety that we see. All right, let's zoom in a bit on the Cascade Range. This is your Northwest America, Southwest Canada, British Columbia, Washington, Oregon, North California, stuff like that. Of course, the most famous volcano of this area is Mount St. Helens. If you're old enough to remember, if you remember the explosion, or more likely you've heard about the explosion in, I think, 1982, a lot was going on there. What you're looking at the right side of this image is basically the Cascadias. The Pacific Ocean and North America are running into each other. The Pacific Ocean is going underneath. As it goes underneath, it heats up, it melts. That melted magma works its way up through the Cascadias and produces, for example, Mount St. Helens. Mount St. Helens was unique because it was essentially in America. And volcanologists had been studying Mount St. Helens for a long time. So you have a very detailed story of the eruption of the volcano. Starting in early March, unrest features were felt. Minor earthquakes, minor eruptions, outgassing of volcanic gases. As this activity started out in early March, you notice a change, a bulging in the volcano. See there on the left? Now look at it here, right? The volcano started to distort as the machine that is Mount St. Helens started to gurgle up and produce this pressure. The buildup in pressure causes deformations as shown there, growing, and growing. And volcanologists are able to record this in amazing detail as it grew over time. Eventually, May 18th happened. You have a moderate earthquake that triggered a massive landslide on the north side of the volcano. This massive debris avalanche earthquake very well could have been caused by Mount St. Helens in the first place, clogged up streams, released pressure of near-surface volcanoes, and produced a lateral blast at the initial sideways interruption to the north. That lateral blast produced a later vertical eruption, as shown here, and Mount St. Helens explodes. What you're looking at there. That picture should look familiar, right? So here's a concept test. Pause if you want to do it. But yeah, there's a whole lot of steps that were very precisely recorded, showing exactly how and where Mount St. Helens erupted. Because that bulge you see on the left there is that bulge you see sort of on the right of the diagram at the top. And then when that bulge broke, it was the vent that released the pressure that allowed the eruption to take place. A vertical eruption column, being that down to the bottom, rises 12 miles within 10 minutes of initial eruption. 12 miles after 10 minutes. That's how much pressure is built up under Mount St. Helens. Amazing, right? So, last chapter we talked about measuring earthquakes. Well, we measure volcanoes too, actually. The Volcanic Explosive Index, or VEI, measures the volume of erupted material. It's 8 divisions on a log scale. Remember, a log scale is every step is a larger increase than the one previous. So there's a bigger difference between 2 and 3 than there is between 1 and 2. If you look at the VEI index or VEI measurements, you see that Mount St. Helens ranks about a 5, Nevado del Ruiz ranks a 3, and that one at the bottom there with the outgassing in the Congo ranks about a 1. So there's a bigger difference between 5 and 3 than there's between 3 and 1. They're not equal steps. When a volcano erupts, what happens? Well, we previewed a bit of this before, but a volcano is not just the lava and the magma. There are lots and lots and lots of different components to a volcanic eruption that are of significant importance to humans. The biggest one, of course, is your tephra and your gases, your lavas and stuff like that that come out that everyone knows in pictures when they picture volcanic eruption. But There's more to it. The first big one, of course, would be landslides and pyroclastic flows. Your landslides are your destruction, shown here, your destruction of your mountain. That all goes downhill. Anything below it does not survive. Picture back to Columbia, right? Your pyroclastic flows are the lighter dust and debris from the explosion. You're heating up all that ice and snowpack, right? That's mixed in the mud, and you're getting superheated, super fast dust that's full of little teeny shards, glass-like shards of rock flying down the mountain in all directions. You get caught up in a pyroclastic flow, you're not happy about it. But there's more to it. The lahars that can come across from the destruction is also very important, because the lahar is sort of the muddy version of the lava flow, and it can travel longer distances because it's not the magma. It's like a combination of a magma flow and a landslide, and it can clog up rivers, and it can destroy entire ecosystems. But beyond all of that, the eruption cloud itself can cause further downstream effects, such as acid rains. If you get that eruption cloud up there, it hits into the lower atmosphere, travels all over surrounding the volcano. It can have severe effects on the environment. Mount St. Helens, for example, when it blew up, it reduced the total height of the volcano by some 400 meters. Where do you think that 400 meters of material went? Everywhere. It went up into the atmosphere, it went all surrounding the volcano. That's 400 meters tall of mountain, very wide mountain, gone, now spread everywhere. There's if you get the chance to look up David Johnston here, he is I believe that's the name of the guy. He is a very famous story of someone who was at Mount St. Helens when it actually erupted. And I'll just let you, if you want to, go Google, read about that. But here we have some before and after pictures. Notice the lack of trees here. This is these pictures of from a similar distance. So these before and afters, one's not zoomed in. It's impressive. That's the power of a volcano, right? But of course, there's always more to the conversation. Here we can see in the bottom here, mud flow, lateral blast, debris avalanche, and pyroclastic flow results, right? So the mud flow is start here and there, everything that's missing, going down the mountain, landing someplace. And it went, as you can see here, followed riverbanks, went everywhere. The debris avalanche, same song and dance, but that's your heavier material that's more connected with your snow. Your pyroclastic flow, that's your super hot stuff that as I just said, is superheated and it's going to flow everywhere. But your lateral blast deposits, those are interesting. Those can destroy objects up to 12 kilometers away, knock down trees more than 25 kilometers away. And you can see here, because the way the orientation of Mount St. Helens when it blew up shot material in one direction. Notice the back corner of the volcano is still there. So it shot 400 meters plus the side of a volcano out to the north, demolishing everything in its way, including Spirit Lake. Right? Look up pictures of Mount St. Helens. Go watch a full-length documentary on YouTube or something. It's amazing what happened. All those trees you see there, gone. Right. So what comes out of a volcano? Well, of course, lava and magma, but I said pyroclastic flow earlier. And I said debris flows, avalanches. What are those things? Well, the parts that come out of volcanoes can vary widely, but are all interesting to know about. For example, here we have pictures of volcanic bombs. The volcanic bomb is a big chunk of material that is just flown out. And it can be the size of your fist or the size of a car. And the particles blasted from the side of the volcano. Here you can see volcanic ash. This is kind of like breathing sand. You don't want to do it, and it coats literally everything. Here we can see the picture on the top there of Mount St. Helens, the actual ash itself traveling across over to Idaho into Montana. And that was in 1980. But we have recorded evidence of ash flows from, say, Yellowstone that cover the entire half of the United States. So again, think about what we were talking with Mount St. Helens, how big that explosion was, and look at that yellow line at the top there. That's its ash flow. And compare that to the ash bed sizes of Yellowstone. Think about how big Yellowstone is when it explodes. So these I'm never good at this word. Tephra, I think is what it's pronounced. These tephra represent, again, the particles that blast in the air by the eruption. And they can vary in size dramatically from powder, well, dangerous, deadly razor sharp powder like volcanic ash, up to rocks the size of cars being thrown miles away. Of course, you can also talk about the volcanic gases. We talked about that a bit before when we previewed it for a conversation about the lake in Africa. But volcanic gases, just water vapor, sulfur dioxide, carbon dioxide, have major effects in the surrounding climate. Sulfur dioxide, for example, can block insulation and temporarily reduce global temperatures. If you get a chance, look up Summer Without Sun in Europe, where essentially a volcano in northern Africa erupted and covered the entirety of Europe so densely with volcanic ash and clouds that the sun didn't exist for like an entire summer, and everyone thought the world was ending. It's ridiculous. And then, of course, widespread release of carbon dioxide at higher temperatures due to fast rates of volcanism produce very serious results. Global warming, right? That is the direct result of the increased amount of gases in our environment. Lava, the big one, the one everyone knows, right? We talked about the variety of lavas that are out there, from super explosive lavas at the top to rather smooth, fun. You can like walk in front of the lavas at the bottom. Your low viscosity lavas can flow up to 50 kilometers from their source, right? That's a long distance. It's like, what, 35 miles? And they tend to, follow the path that water would follow because lava is a fluid. And your higher viscosity lavas tend to remain closer to the volcano, again, because they're not going to flow as well by definition. They're highly viscous, but they're still super hot and super dangerous. And when these lavas are shot out in the explosion, these lavas are shot out in the explosion. And of course, we talked about the pyroclastic flows. These are dense clouds of, again, particles. You can think like superheated sand. Essentially, would be a good analogy. It's not sand in there, but it's a close enough example. Volcanic gases that move super fast and are dangerously hot. Here we have a picture down below of a pyroclastic flow that flowed through a town. I think in the early 1900s is when this picture was taken. Completely decimated a town. What you gonna do? It's dangerous, scary stuff. Lahars, of course, are the mud flows that are created by the volcanic debris. Essentially, the volcano erupts, melts the snow and ice pack on the side of the mountain, mixes with the slurry of the volcanic material, flows down the volcano, usually enters a river stream, for example, as shown here. Look at the size of those trees compared to that person, and flows on down and clogs up the river. So everything in the river is dead too, and you get no river flow. Here's a picture of Mount Rainier. This is a mountain close to Mount St. Helens. I think we got a picture of it. We don't? Okay. This is in, I think, also still in Washington. And you can look at what river channels come from Mount Rainier. And if Mount Rainier ever explodes, which it's technically supposed to, if it ever explodes, what's going to be covered up? What rivers essentially can be destroyed by the eruption? There's a lot of them, right? Rivers are still the lifeblood of humanity. Here's another concept test. Again, feel free to pause if you wish. All right, cool. That's lava explosions. Let's back it up a bit here and talk about something a little less dangerous. What volcanoes actually look like. In general, there are three types of volcanoes: shield, strata, and cinder cones. These volcanoes range in size and range in how common they are, and also range in how dangerous they are. And there's also other volcanic landforms like calderas, lava plateaus, geysers, which we'll talk about as well. Shield volcano is the classic volcano. It's the volcano that you picture when you picture a volcano. No, wait. Oh, I'm sorry. Back that up a bit. Stratovolcanoes are the ones that you picture when you picture a volcano. My bad. Mount St. Helens was a stratovolcano. It's the classic, also known as a composite volcano. Shield volcanoes, as shown here, get their name because they look like they're giant, flat shields of mountain. Like a shield volcano is so large, you're talking like the Hawaiian Islands. Each one of those is its individual shield volcano almost. They're broad, gently sloping, and they're not very explosive. Since they're so big, they are able to disperse the pressure more evenly and not have violent eruptions. This, of course, is different from a stratovolcano, which is sort of like a pimple and compresses all that pressure into one thing and builds it up over time. The pressure and the slow release of the lavas and magmas upwells the crust itself, forming the stratovolcano, causing, again, your Mount St. Helens, your Pompeii's, stuff like that. And cinder cones are little teeny volcanoes that pop out of the sides of things. They are like this example here, right? You got very large volcanoes. You got these little dots around here. These are your cinder cones. They're short-lived. They're not nearly as big. Again, up to 400 meters, which is the top of Mount St. Helens is 400 meters. And here, volcanoes are usually, these cinder cone volcanoes are usually smaller than that. And they're sort of the places where pressure is released before the big explosion happens. Cool. So those are the three main types of volcanoes: shield, strata, cinder, right? But when a volcano erupts, or when a volcano is going to erupt, there's other various landforms that we associate with them. One of these is called a caldera. A caldera is a giant crater that's formed when a volcano collapses. Picture Yellowstone, for example. And the reason a caldera forms is, well, under the volcano is this massive amount of pressure. When you release that pressure, in collapses the mountain. That collapsed in mountain is what we call a caldera. Not the best picture of one, but hey. Lava plateaus, these are the gigantic results when the lava spews out everywhere. Eventually it cools down, it hardens. That's what you get, a lava plateau. Again, these things are very, very common. Lots of the unique geology of, say, the American West is a direct result of lava plateaus and the hardness of those rocks not weathering, not eroding as much as the surrounding environment. We'll talk about weather and erosion, I believe, next chapter, actually, so you can get a better understanding of that. But what you're looking at here, the entire like south of Washington, a big part of the north of Oregon, that's one gigantic basaltic lava flow. That's the result of a few volcanoes in the region just letting out lava and magma consistently for maybe tens of thousands of years. And these things are everywhere, as I said before. When they're really large, you call them traps, Deccan traps, Siberian traps, shown here. And they're just the result of lots and lots and lots of ongoing volcanology producing massive amounts, massive plateaus, massive beds of volcanic material. Geysers, hot springs, mud volcanoes, things along those lines. These are other ways in which the volcano can release pressure. Usually they're associated with water in some way. Again, think Old Faithful as a hot spring, or a geyser, sorry, right? And the kind of Mammoth hot springs, of course, as well in Yellowstone National Park. And they, when you picture volcanoes, and again, I say this a lot in this class, right? Geology tends to work the way you think it works, at least at this level. So what do you think is causing all the explosion of the water? Well, probably the magma, the hot magma underneath, boiling water up and it's escaping. That's exactly what it is. Why is the water in a hot spring so hot? Because it's being fueled by the magma underneath it, right? Cool. So that was all volcanoes. But the world's not just all volcanoes, right? There's mountain chains, and within those mountain chains, you have a few separate volcanoes. So let's talk about mountains for a bit now. Mountains, the thickest crust, where the thickest crust in the continental crust takes place. We'll get to why that is here in a bit. The Himalayan mountain range, top to bottom, is some 70 kilometers thick of crust, whereas normal crust, like not at a mountain range, is about 40 meters thick. And the Himalayan mountains are not 30 kilometers tall. Okay. So the crust below them, below the Himalayas, is also super, super thick. We tend to find younger, higher mountains along convergent plate boundaries, like the Himalayas. And then we tend to find older mountains where there used to be convergent plate boundaries, such as the Appalachians. And here we can see various convergent plate boundaries as shown here. And all along this orange lines, we also find mountain ranges. We find mountain ranges that aren't there. We then therefore believe that indicates there used to be convergent plate boundaries along those points, because all mountain ranges follow these plate boundaries very well. Ocean kind of convergent plate boundary. What you're looking at here is a picture of the movement of the Indian subcontinent and the creation of the Himalayas. So you have on the left here India, and it just broke off from Africa some 160 million years ago, something like that, and just drove straight into Eurasia, just smashed right into it. And as it does that, as it comes collapsing in, all the crust in between Eurasia and India buckle up. And this buckling up that happens creates the Tibetan plateau, creates the Himalayan mountain range. All that ocean in between there gets crumbled up and forms what we have there in the center. And that's what happened with India. That's what created the Himalayan mountain ranges. And then within that, you can have, of course, lots of different faulting, normal inverse faults, and lots of breakage. Everything we're looking at, that's what all those black lines there are, different breaking within the plate structure itself to create the variety that we see in the Himalayas. All right. So when I said earlier about mountains being the heaviest, mountain ranges being the thickest crust, what I'm referring to is what's known as isostasy as a result of density. So if you put a block of water floating, right, you're going to notice, in this case, oak, apparently, you're going to notice that it's not going to float all the way on top. It's not going to sink, right? It's going to be buoyant at some level, usually about halfway through the block. And this is because, of course, the various densities of what we're talking about here. Most woods are less dense than water, so they float. And the amount of density difference between the two dictates how high or how low they float. Icebergs, they say 80% of the icebergs are underneath the water, because icebergs are very heavy density-wise because they're made of water. So they float a lot deeper than, say, a piece of wood. But if you have something heavier, let's say this oak here, which is, okay, so that's supposed to be pine, not oak. Bad subtitle here. The pine is floating 50-50, but the oak is denser, so the oak floats deeper down. Since it floats deeper, because it's denser, a lot more is on the bottom than on the top. This idea goes to explain the continental crust and the thickness under mountains. Since you're squishing all that mountain range together, again, go back to these pictures, since you're coming together and you're squishing the continents and smashing them together, you're getting a lot of continent stacked on top of itself. Continent is very heavy, so it sinks down, creating very thick continental crust under, say, the Himalayas. When you don't have this piling on of the continent on top of itself, you get regular continental crust, which is your 40 meters thick, and then your ocean crust, which is your less dense stuff, therefore doesn't fall as deeply. Sorry, your ocean crust is more dense, but it's thinner, so it doesn't fall as deep down. A lot, right? I know. I'm not a big fan of teaching isostasy at this level, but the book likes to do it, so I went through it. Cool. Now we're coming to the end of the chapter here, the rise and fall of mountains and temperatures. Changes in elevation depend on the relative density of the crust and mantle. We talked about that before. So elevation change tends to only account for about 20% of added removal material. Most change in the crust or root occurs below the surface. The more layers you add, more stuff you build upon for the crust, the deeper the bottom part of it sinks. Again, as shown here, you keep adding and removing layers, you're not really adjusting the elevation above water that much, but you're adjusting the elevation below water quite a bit more. So when you are dealing with mountain chains, the way the mountain chains react, given the fact that they're destroying the crust as much as they are, these changes in mountain chain, these changes in the buoyancy essentially of the crust due to how thick it is, has effects on sort of everything going on above and below the surface. Here we have examples of the differences in erosion. On the left, we have regions that erode into valleys and mountains. And on the right, we have uniform erosion. And then as the things bounce up and down, again, according to the isostasy and the way that this happens, essentially in the right and the left there, you have more buoyancy and you're having more varied depth of erosions. So what does all that mean? Well, about for every 1,000 meters of rock eroded from a mountain, isostasy, or the bounce, the buoyancy of the crust, results in just 200 meters decrease in elevation. So you can have very, very tall mountains, a lot coming off of them, and the mountains can still be very, very tall. Again, to go back to this picture here on the bottom right, there's a lot more crust in the mountains than there are in other places. So there's a lot more to be eroded than just what your eyes see. That's the point it's trying to get at there. Mountains are such long-lived features because there's a lot more below the mountains than there is above the mountains, because the mountains themselves cause that incredible stack of material. So they keep going and going and going. Mountains are very, as I said before, long-lived features. The Appalachians are super, super old, right? So if you have approximate erosion rates of, say, 0.1 to 0.2 millimeters a year, which of course is dependent on many factors, it takes about 5 to 10 million years to erode about a kilometer of rock. But if you erode a kilometer of rock, you replace about 80% of that due to isostasy. So in about 5 to 10 million years, you lose a kilometer of rock, but you only visibly notice a 200-meter difference. So it takes about 50 million years to erode that same kilometer of rock, but you're getting 80% more total stuff out of the rock. So again, we can look at the Himalaya mountain range, right? We have warm, moist air from the Indian Ocean rising over the Himalayas, forming monsoon rains. These monsoon rains feed the rivers that erode the mountain, and the sediment from all this is deposited in the Bay of Bengal and the Arabian Sea. So these mountains are influencing their own climate. Monsoons are stripping carbon dioxide from the atmosphere, moving CO2, etc., etc. The mountain range in general is having a very large impact on the earth, and it will continue to, because the mountain range simply exists. Geology is a major factor in everything, right? Most people, rocks are rocks. They've been here now, they've been here forever. Who really cares? That's not how this game is played. Geology affects the biosphere, which affects the hydrosphere, which affects the atmosphere, which affects the geosphere, which affects everything. It all interplays wonderfully. The exosphere, it's the sun's energy and stuff like that. So understanding how important geologic features are to our day-to-day existence will go a long way in helping us solve the problems that we have. All right, that was a lot. I know. I get it. Ask me any questions in class. Comment down below if you got anything. Shoot me an email. Do what you need to do. Thank you for listening to the presentation. Take care.